Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Carbon nanotubes can be used in lithium-ion batteries to unlock higher energy densities and faster charge rates. The question is, will such a difficult-to-manufacture and expensive material ever actually be used in mass-produced lithium-ion batteries? Much to my surprise, it's already happening, and for me, it's rewriting the script on one of the technologies that Tesla teased at Battery Day. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. Let's start by taking a look at the roles that carbon nanotubes can play in lithium-ion batteries. When the electrode foils of a lithium-ion battery are coated at the factory, the coating is made of a powder mixture that contains three ingredients: the active material particles, which make up about 95% of the powder or more, and about 5% additives. The two additives are carbon black, which improves the electrical conductivity of the electrode, and polymers that help hold the electrode film together and stick to the electrode foil. Carbon nanotubes help with both binding and conductivity because they're orders of magnitude more conductive than carbon black powder, and due to their stretchy, string-like nature, they can help hold the electrode film together. That is, carbon nanotubes can be used as a replacement or in conjunction with existing additives to increase the performance of lithium-ion batteries. That's backed up by a paper from Jeff Dahn's lab, which is Tesla's research partner, titled Optimization of Silicon-Containing and Silicon Oxide-Based Anodes with Single-Walled Carbon Nanotubes for High Energy Density Applications. The conclusion of the paper says, quote, "The strong positive effect of carbon nanotubes is undeniable, even when used in small amounts. The use of carbon nanotubes in silicon oxide graphite composite electrodes in an amount of only 0.2% allowed the use of any binder to enable good capacity retention over 100 cycles. Although not inexpensive, the addition of these carbon nanotubes allow the use of simple binders that favor slurry processing to reduce cost. This data shows that overall electrical conductivity of the anode through the use of single-wall carbon nanotubes is an important part of maintaining anode capacity in high-volume expansion active material." End quote. Translation: although carbon nanotubes are expensive, they're potent and can be used in tiny amounts in standard processes and with simple binders, which makes them commercially viable. Furthermore, carbon nanotubes could be very useful for anodes that use high loadings of silicon. Higher loadings of silicon are the next likely step for increasing the energy density of lithium-ion battery cells. But due to the fact that silicon expands by several 100% when the battery charges, it causes the electrode to disintegrate. Currently, the loading of elemental silicon in lithium-ion battery cells is limited to about 4% by weight. But increasing that to 20%, for example, could increase the energy density of lithium-ion battery cells by 20%. The research that Jeff Dahn's lab has done on nanotubes and the fact that they're Tesla's research partner made me rethink my initial analysis from my Battery Day series. In Tesla's Battery Day presentation, they said that they would use a highly elastic binder to help deal with the expansion issues from silicon. At that time, I concluded that Tesla might use polyrotaxanes, or self-healing polymers, for the binder. Now that I've researched carbon nanotubes, they seem like the better choice. That's because carbon nanotubes can be used at less than 1% of the electrode by mass versus the 5% that would be necessary with polyrotaxanes. That 5% of additional material would mean about a 2 to 3% energy density penalty, which would negate some of the positive energy density benefits of using silicon. Furthermore, the availability of carbon nanotubes has increased greatly in the past 5 years since Battery Day. In 2020, there wasn't yet a large-scale supplier of the type of carbon nanotubes that Tesla would need, but that's now changed. With all that background on nanotubes in place, let's get more specific on factors like performance, cost, and scalability. With regards to performance, it's important to start by teasing out the specific type of carbon nanotubes that I'm referring to in this video, which are single-wall carbon nanotubes. Single-wall carbon nanotubes have, as the name indicates, a single wall, and multi-wall nanotubes have several layers of walls. As far as I'm aware, Oxyal has the best publicly available slides and information on carbon nanotubes, so I'll be using several of their slides today. To be clear, Oxyal hasn't sponsored this video. The only sponsor I have and have ever had is Rebellionaire. As you can see on screen, single-wall carbon nanotubes have a clean and long structure. That's as opposed to multi-wall carbon nanotubes, which have a structure that's gnarled and tangled. Single-wall carbon nanotubes are more difficult to manufacture, but it's worth it. As the paper from Jeff Don's lab points out, they're highly flexible, have strong adhesion, and show huge tensile strength. By comparison, multi-wall carbon nanotubes are less expensive, but are often stiff and short with much less adhesion strength. The takeaway here is that single-wall carbon nanotubes are far more potent as an additive and can do things that multi-wall carbon nanotubes simply can't. For example, due to their conductivity, flexibility, adhesion, strength, and length, single-wall carbon nanotubes are uniquely able to loop through the electrode film, providing both a conductive electrical network and reinforcing it against expansion and contraction forces. Why does that matter? As this image from the Don research paper shows, for a 92% silicon anode with no carbon nanotubes, after 100 cycles, the test cells have about 150 mAh per gram of capacity remaining. With 0.25% single-wall carbon nanotubes by mass, there's about 1,000 mAh per gram of capacity remaining after 100 cycles. And at 0.5% by mass, degradation remains relatively flat and is minimized after 100 cycles, with 1,300 mAh per gram of capacity remaining. Adding more nanotubes to 0.75% had minimal further beneficial impact. What this means is that single-wall carbon nanotubes could unlock higher loadings of silicon in the anode to increase energy density. But to be clear, as Tesla showed at Battery Day, other technologies will also be required as well, such as a polymer coating on the silicon to keep it from reacting with the electrolyte. What about electrodes that don't use silicon? Would using single-wall carbon nanotubes provide any benefits? Yes, in three ways. First, due to their higher conductivity, single-wall carbon nanotubes lower the resistance of lithium-ion battery cells. That reduces heat generation, allowing the battery to be charged and discharged more quickly without increasing thermal strain and therefore causing degradation. That effect wouldn't be dramatic because most of the resistance in a battery cell is from the ionic resistance. But the improved electronic conductivity from carbon nanotubes might be good for a 10% improvement in charging speed. Second, due to the strength and flexibility of carbon nanotubes, the electrodes can be made thicker without cracking. Thicker electrodes mean higher energy density battery cells because it increases the ratio of active to inactive material. Again, the impact wouldn't be huge, but 5 to 10% higher energy density wouldn't be unreasonable. Third, by replacing the 2 to 3% carbon black that's used in conventional electrodes with a fraction of a percent of nanotubes, the dead weight that's removed could increase the energy density of the battery cells by about 1% or so. That is, there would be benefits to using single-wall carbon nanotubes in conventional chemistries, but most of the benefit of nanotubes would come from unlocking the potential of higher silicon battery cells, with up to 20% greater energy density over time. Let's move on to cost. Oxyal provided cost reference figures, which are on screen. They claim that battery-grade carbon black is $7 per kilogram, and 1 to 3% by mass is needed in the electrode. That multi-wall carbon nanotubes are $50 per kilogram, and 0.6 to 1% is needed in the electrodes, and they're indicating a price of $1,000 per kilogram at volume for their single-wall carbon nanotubes, which, depending on the application, only around 0.05% is needed in the electrode. Why does Oxyal suggest 0.05% carbon nanotubes by mass for the electrode, and Jeff Dahn's research showed that 0.5% is needed? It's because the tests in the research paper were run on anodes with a 92% silicon loading, which is extreme. For a more reasonable 10% silicon loading, only a 0.05% loading of carbon nanotubes is needed. That is, roughly an order of magnitude less silicon requires an order of magnitude less nanotube material. As a side note, I checked up on Oxyal's cost figures using Grok Deep Search, and all of them came up higher, even the carbon black. My assumption is that's because Oxyal is using information that's more up to date than the publicly available information that the AI is drawing from. All of these industries are scaling fast, so it's expected that the prices that are being privately quoted to bulk customers are dropping year by year. But if you have better cost figures, let me know in the comments below. With that in mind, even though there is potential for bias here, I'm going to consider Oxyal's figures realistic, but take them with a grain of salt. Moving along, whether the application is for conventional lithium-ion battery chemistries or one that uses a high silicon loading in the anode, Oxyal indicates that single-wall carbon nanotubes cost about $1 per kilowatt-hour. That's as compared to 20 cents for carbon black and 60 cents for multi-wall carbon nanotubes. That is, not cost prohibitive. In fact, if single-wall carbon nanotubes enable high-energy density silicon anodes, the reduced battery pack weight could actually end up saving money. For example, if the battery pack in the Tesla Semi is 900 kilowatt hours, carbon nanotubes would add about $720 to the cost of the pack. That would cut 529 kilograms of mass from the battery pack. That means over the 1 million or so mile life of the Semi, half a ton of additional cargo could be carried on each trip, or half a ton less mass being dragged around that causes wear and tear on the tires and powertrain. In the case of Tesla's premium vehicle trims, like the Model S or Cybertruck, it could allow, for example, 10% more range at a cost of $70 to $86 on a 100 to 123 kilowatt-hour battery pack. That could also apply to versions of the Model 3 and Y, but for mid to low-cost vehicles, the extra spend may not be worth it, especially for commercial use cases that are cost-sensitive but not mass-sensitive, like the Cybercab. Next, what about scaling? I found a number of companies that are producing single-wall carbon nanotubes at gram to kilogram scales, but no other company besides Oxyal seems to be producing them at the scale of tens of tons per year or more. In 2024, they completed a production facility with 60 tons of annual production capacity. That is, they have a full-scale commercial production facility that's already operational. Beyond that, they have plans for 240 tons of annual production capacity by 2026 and 1,000 tons of annual production capacity by 2030, with continued scaling from there. The question is, how many EVs is that enough for? According to this slide from Oxyal, which I double-checked the math on, the average EV uses about 3 to 4 kilograms of carbon black, and that could be replaced with about 100 grams or 0.1 kilograms of single-wall carbon nanotubes. That means 1 million vehicles requires about 100,000 kilograms or 100 tons. So Oxyal currently has nanotube production capacity for about 600,000 vehicles per year, with plans for 2.4 million vehicles of production capacity by 2026 and 10 million vehicles by 2030. That is, they already have plenty of capacity in place for one medium-sized EV maker and plans for enough production capacity to supply several large EV makers like Tesla. And I don't doubt that in the coming years, that other companies will follow suit to build a broader-based and more competitive single-wall carbon nanotube supply chain. This brings us to the last question of the video. Will Tesla use single-wall carbon nanotubes? As I've shown in the past, spider silk-like threads can be seen in the anode of Tesla's 4680 cells. However, that's been confirmed through chemical analysis by UC San Diego to be the PTFE or Teflon that's used in Tesla's dry coating process. PTFE is flexible and has some strength as a binder, but it's an electrical insulator. The ideal material for binding high silicon anode would be much stronger, flexible, and electrically conductive like carbon nanotubes. However, PTFE can't be replaced with carbon nanotubes because it's necessary for the dry electrode coating process. It turns the electrode powder into a kind of dough that can be laminated onto the electrode foils. So, if the PTFE can't be replaced, could Tesla still add carbon nanotubes to the powder mixture to provide additional binding capacity and electrical conductivity? According to Tesla's patents for the dry coating process, yes. Does this mean that Tesla will use single-wall carbon nanotubes in their batteries in the future? I'm not sure, but in my view, so far, they're the best candidate yet for the filaments that Tesla showed in their silicon anode illustration at Battery Day. The sticking point for me is that Tesla doesn't like to be reliant on a single-source third-party supply because it creates supply chain risks. Additionally, it's likely that Tesla doesn't want to be in a situation where the supplier is wagging the dog. The only solutions I see to that are for Tesla to vertically integrate into carbon nanotubes, wait for the nanotube supply chain to expand, or buy a controlling share in a nanotube manufacturer. They could also become the primary customer of Oxyal with huge material supply agreements like Tesla at one time did with Panasonic, but that could be risky. With that said, those risks could be mitigated if Tesla had employees embedded and working with the team at Oxyal. As a final note, I did double-check with people in the industry about whether carbon nanotubes are currently being used in lithium-ion batteries, and they are. That is, carbon nanotubes are no longer a future technology, but an off-the-shelf technology. That's particularly true with multi-wall carbon nanotubes, which are already being produced in the tens of thousands of tons per year. In summary, single-wall carbon nanotubes are here and already used in lithium-ion batteries. For conventional battery chemistries, they provide more of an incremental rather than revolutionary improvement, with lower resistance for slightly faster charging speeds, thicker electrodes that could lead to 5 to 10% more energy density, and a reduction in dead weight in the battery that could increase energy density by about 1% or so. However, where single-wall carbon nanotubes appear to be uniquely useful is for future battery chemistries that use higher silicon loadings, which could provide a base for the next 20% of energy density increases that we'll see in mass-produced automotive EV battery cells in the next 5 to 10 years. If you enjoyed this video, please consider supporting the channel by using the links in the description. Also, consider following me on X. I often use X as a testbed for sharing ideas, and X subscribers, like my Patreon supporters, generally get access to my videos a week early. On that note, a special thanks to my YouTube members, X subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.